Hi everyone, this is Scott Reaves. This is Protein Lecture 2 for our senior project class, and this is a lecture overview that I want to cover in this PowerPoint. Hopefully this won't be too long. I think maybe you've heard me say that before, but I'll try to keep this kind of short. Let's look to the bottom of this. Now this information is based mostly on Chapter 3 of Protein and Exercise in a textbook kind of manual called Sports Nutrition, a Practice Manual for Professionals. And this is written by two individuals named Nicholas Bird and Stuart Phillips. And this is all posted obviously, but Stuart Phillips is one of the best guys in protein and amino acid metabolism in research right now. And he's been around for quite a while, came out of a great lab, and an individual that's kind of been one of the pioneers in establishing protein requirements. And Phillips has had a great career, and he's still very active in this area. So he provided this kind of review or overview of protein requirements in this book. So I thought this is a great reference for all of us. So here's the overview. We're going to talk about muscle protein metabolism really quickly, and what happens during resistance and endurance exercise, and we'll talk about protein timing and the in relation to both resistance and exercise. You can see right away there's a pattern of this, kind of the two modes of exercise that we'll be looking at, resistance and endurance exercise, have different effects on protein metabolism and therefore have differing effects on protein requirements in quite a few different ways. So we'll keep kind of going back and forth between the types of exercise. And when you're making recommendations to individuals, you want to try to characterize their types of activity because that can drive how much protein they need, I think, obviously. But one of the tricky parts is, you know, if a person's doing both, then how do you make those recommendations? So we'll talk a little bit about that. Then we'll talk about the importance of leucine levels, protein quality and protein quantity, and then whether or not ingestion of single amino acids are effective in this entire paradigm. So muscle protein metabolism. Now originally it was thought that the energy used for muscle contraction was actually from the explosive breakdown of protein molecules. And if you look at the way some people go about protein intake, you would think that that's still the case, that people think anytime they do any type of demanding exercise on muscle tissue, that protein is the energy source and the source for recovery, and all of the requirements can be met by increasing protein. And hopefully by now we know that isn't the case. But it does increase protein requirements when a person exercises, especially during specific types of exercise. But if we also think about the actual use of protein for energy as overall percentage, it's actually relatively low, and probably a ballpark number is something like amino acid oxidation probably provides about 2 to 4% of overall energy during most types of exercise. So it's still a small energy source. So it's more about the other functions of protein than it is for energy. I think we all know that. And the role of branched chain amino acids in this is unique because muscle tissue has the ability to oxidize branched chain amino acids more so than other tissues like the liver. So there is a specific role of branched chain amino acids as an energy source in muscle tissue. And remember, the branched chain amino acids are leucine, isoleucine, and valine, and they are essential amino acids, and muscle tissue can oxidize those as an energy source during aerobic activity. The essential amino acids, or the branched chain amino acids, also have a role in protein synthesis, of course, and that takes place throughout the body, but oxidation takes place mostly in muscle tissue of the branched chain amino acids. So we'll talk about those a lot more as we go through this. And remember, although protein is not a significant energy source, the effects of exercise on muscle metabolism are significant. So for example, exercise increases protein turnover in muscle tissue. It stimulates muscle protein synthesis, it stimulates muscle protein breakdown, and the combination of those, synthesis and breakdown, overall determine whether or not a person is going to be adding muscle or losing muscle based on their exercise. So we're going to look at this in a few different ways. Remember, this is the what I just mentioned, the muscle protein turnover. It's a balance of muscle protein synthesis and muscle protein breakdown. And there are distinctly different effects on each of these for resistance and endurance exercise. Now, for example, if a person is doing resistance exercise, it tends to stimulate muscle protein synthesis and breakdown to a significant effect. And the types of proteins in muscle that are mostly effective during resistance exercise tends to be the myofibrillar proteins, the contractile proteins, in other words, mostly actin and myosin. In endurance exercise, there can be significant effects of both muscle protein synthesis and muscle protein breakdown. But in that case, especially for the muscle protein synthesis, in endurance exercise, it's going to tend to be more about proteins such as mitochondrial proteins and energy-providing proteins and proteins that are involved in oxidation of some of the amino acids, more so than the contractile proteins. That's just basic statements there and effects. So turnover is constant, but it's affected by food intake and exercise, right? So we know that overall during the day, we are consistently turning over the body's proteins, including those in skeletal muscle, and that overall, this can be affected by food intake and exercise, where each can be accentuated and affect the balance, but muscle net protein balance equals muscle protein synthesis minus muscle protein breakdown. In a person that is not adding a lot of tissue or muscle, most of the time, over time, the muscle net protein balance is generally zero. Right? In that case, protein synthesis equals muscle protein breakdown. But that muscle net protein breakdown tends to be different at rest and in the fed state and after resistance exercise. So each of those conditions affects that net protein balance. And it's important that a person realizes that exercise affects protein metabolism and can actually put a person in a negative net protein balance. In other words, they can actually lose muscle until they use nutrition to actually kind of reverse that effect and allow anabolism to take place as part of the recovery process that we talk about so often. So here's an example. This is a figure out of the chapter, and it shows the muscle net protein balance at rest and after feeding and resistance exercise. So it says, and this is an important point, that resistance exercise is fundamentally anabolic, such that net protein balance becomes less negative in the fasted state. Now, the inset illustrates training-induced change in lean body mass that manifests from the synergistic effect of feeding dietary amino acids and exercise. However, in the absence of an anabolic stimulus, lean protein mass remains essentially unchanged, such as in sedentary individuals. Okay, and then there are some of the abbreviations. So let's look at the graph here, and hopefully you can see the cursor. This is muscle net protein balance, so we have negative and positive on the y-axis here. And in the fasted state, in general, we have the individual in a negative muscle net protein balance. In other words, breakdown is more significant than synthesis. if a person is fed, and we're going to say this is a mixed meal including a protein source, that muscle net protein balance tends to become positive. Okay? Now if we look at the next one, so in other words, there is some of an anabolic effect just because of the ingestion of specific nutrients. In this case, we have an exercise scenario, oops, right here, in a fasted individual, and the muscle net protein balance becomes negative, although it's less negative than in the sedentary individual because they have exercise, so there's some stimulus, but you can see it's still negative until that exercised individual is fed. And in that case, you can see how much more significant the combination of that exercise and feeding is relative to just a fed state in a sedentary individual. So they obviously are synergistic, and that's one of the points that's being made here. And these are, of course, dietary amino acids, and we'll talk about some details as we go through this. And for example, if you look over here, what it results in is a % change in lean body mass, sedentary individual, no change, whereas the exercised individual, there tends to be an increase in lean body mass. So obviously, I think we all know this, the combination of nutrition and exercise is a lot more significant than either one of those alone. Now, let's do a very quick review on this and what goes into muscle net protein balance. When we talk about muscle protein synthesis, and let's say we're talking about within muscle fibers, muscle protein synthesis can be regulated at several levels. There is the level of transcription. And so let's think about what's happening here, because we're just going to say that, let's say this is post-exercise, post-meal consumption. So this is postprandial after exercise. Some of the things that can increase muscle protein synthesis include the level of transcription. In other words, gene expression of affected proteins can be increased. In other words, more RNA molecules are made. So for example, the genes for the contractile proteins, as well as proteins, for example, that are mitochondrial proteins or proteins of electron transport chain or other proteins like that, can be affected at transcription. One of the other levels of regulation is ribosome assembly can be affected. And in other words, the ribosomes are combinations of proteins that need to be, or that can be increased in amounts, and some of them are activated by things like phosphorylation. So ribosome assembly can be upregulated post-exercise, post-nutrition, and that can actually help the protein translation. So then we could have an increase in protein translation initiation and elongation because of that. The last one here is mRNA half-life. The longer an mRNA molecule stays around, the longer it's available to be translated. That can also be affected by these. If you put any of those into an enhanced mode, or all of them in some cases, you can have a significant increase in muscle protein synthesis. And lots of studies have indicated that's the case. Now, remember, this is a balance. So if muscle protein synthesis goes up, then muscle protein breakdown is the part that is actually kind of counterbalancing that. And muscle protein breakdown occurs by several mechanisms. And we've talked about the first one, and the first one is lysosomal proteolysis. In other words, I think we talked about it before, we use the term autophagy, or autolysis is sometimes the term used. But in this case, what happens is the lysosomes are actually breaking down some of the proteins that were involved in an exercise bout that may have been damaged or affected in some way, and the lysosomes are actually degrading those proteins. That's a very common occurrence in skeletal muscle. There's also another system in place for breaking down proteins in cells, including skeletal muscle, and that's the calpain system. And the calpains are types of proteases that tend to be activated by calcium that can degrade proteins on their own, or sometimes the calpains actually work with the other systems like ubiquitin and the proteasome. So calpains can also be upregulated post-exercise to help in that adaptation phase. And that's the big part of this. As the proteins are stimulated for exercise, some of them are damaged or affected in a way that they are to be degraded so that that muscle fiber, and for example, can respond and become a more effective muscle fiber in performing the type of work or stress that it was put under. So in general, the more strenuous or rigorous the activity, the more these breakdown pathways are activated. And the last one that we'll go into a little bit of detail in is called the ubiquitin and the proteasome pathways, and we'll look at that in a second. But that tends to be the most significant degradation pathway or process in skeletal muscle. So the ubiquitin and proteasome pathway tends to be the most significant in response to exercise. And so it's affected by diet as well. So we'll look at that in a second. This is actually out of your other, the Gropper text that we've used for other classes, although we didn't go into detail on this. I wanted to here because this is an important process that occurs, and if we look at the bottom of this and we see down here the protein substrate. Now that could be an enzyme in the mitochondria, or it could be a contractile protein that has been affected by the exercise regimen or bout. And so now let's imagine this is post-exercise, and how this muscle fiber is going to respond is by it's going to degrade this particular protein and replace it with another protein or additional copies of this protein in order to adapt to the exercise bout. So what happens here is this protein substrate is acted upon by these enzymes, and sometimes they're referred to as, these are enzymes that we called E1 and E2 that are adding a ubiquitin molecule. And so, for example, if we look at E1, this is an enzyme that is using ATP in order to add this ubiquitin molecule. Ubiquitin is, I think it's a 76 amino acid protein that is basically covalently added to the protein, after it's added to the enzyme. So this enzyme uses ATP to pick up a ubiquitin molecule. That E1 enzyme then adds it to sorry, I lost my cursor, to E2, and the E2 enzyme is now picking up a kind of a chain of ubiquitin molecules, and the E2 then complexes with E3, and this ubiquitin ligase complex adds this ubiquitin tail to the protein that needs to be degraded. So E1, E2, and E3 are ubiquitinating enzymes that attach ubiquitin to a protein to target it for degradation. Okay? So they're looking for specific changes in a protein that determine this protein needs to be degraded and replaced. Once that protein has that ubiquitin tail, then that protein is, what should we say, sent or trafficked to the proteasome. And the proteasome is a multi-protein complex that has kind of a hollow core to it that allows these ubiquitin-tagged proteins to enter. And in an ATP-dependent unfolding process, the protein is fed into the proteasome, and the proteasome has enzymes that degrade the protein into peptides and amino acids. And again, this is a very consistently affected protein by exercise. It's affected by other things as well, like aging. A few years ago, we did a study on aging tissue, and we found that in general, overall, and lots of other groups have found this as well, that in general, as we get older, more and more of our proteins have ubiquitin attached, and they tend to be degraded at a higher rate than when we're younger. And again, this is affected by exercise and also starvation and some other things as well, but it tends to be the most significant pathway for protein degradation. So lots of studies have been done on this. But just to give you an idea, this is the process that we're talking about, what happens inside cells post-exercise, and then we're going to talk about how we can actually use dietary protein and some other nutrients to kind of decrease this process of protein degradation and increase protein synthesis and improving that balance toward an optimized effect, I guess you'd say, of the exercise. So this diagram is from the textbook, and this shows down here at the bottom a general overview of the fate of dietary amino acid and protein pools in the body. So these muscle proteins is a collective term referring to the myofibrillar, sarcoplasmic, in other words, that's the cytosol of a muscle fiber, and mitochondrial proteins. And these specific protein subfractions comprise 60, 30, and 10% of skeletal muscle, respectively. So in other words, most of the protein in a muscle fiber are the myofibrillar proteins, actin and myosin and related proteins, troponin, tropomyosin, all of that complex. About 30% is cytosolic proteins, the sarcoplasmic, and about 10% are mitochondrial proteins. Now, each of those can be affected by exercise. All right, but overall, if we talk about, for example, resistance exercise, the most common type of proteins that resistance exercise is going to affect are the myofibrillar proteins. And that's a big part of the overall proteins in a cell. So we have these muscle proteins, and we see these arrows here. We have being synthesized and breaking down overall in this process that consistently occurs 24/7. But we can see that as the protein breaks down, those amino acids enter an intracellular free amino acid pool. Those amino acids can be reused for synthesis, which is very common, or they can be oxidized, which means those amino acids are completely broken down into their atomic components, or those amino acids could leave a particular muscle cell, go into the blood after leaving the sarcoplasm, and be transported to other tissues. But if we look at it the other way, here we have, for example, dietary amino acids that are ingested. They go into the blood amino acids, so that represents a pool. That's a relatively small pool of amino acids. Those amino acids can then go into the muscle cell intracellular free amino acid pool and then be used in this process for synthesis or oxidized. Now here's another part of this. The gut, those dietary amino acids, not all of them are absorbed, of course, and some of them are actually oxidized by the enterocytes and other cells before they even enter into systemic circulation to be a source of amino acids. Okay, so there's lots of different kind of movements or transportation of these amino acids through the different compartments in the body. But it's important that we realize, some of these amino acids are essential amino acids that have to be there for protein synthesis to take place. If those essential amino acids are not there in adequate amounts, then protein synthesis is affected. And even if we degraded some muscle protein in order to liberate some of the essential amino acids, that would not allow us to obtain an adequate supply of essential amino acids. Okay, so we need this constant influx of essential amino acids combining with non-essential amino acids, either from the diet or from metabolism, to sustain protein synthesis at an optimal rate that allows us to adapt to exercise. Okay, so it's really important that we consider things like different types of protein and timing and amounts and all of that to make sure that these pools of amino acids are available to maximize protein metabolism in skeletal muscle. All right, what's next? Resistance exercise. So here's a brief overview of resistance exercise. Remember, we said that it's fundamentally anabolic. In other words, it generally stimulates an anabolic effect. So for example, an isolated bout of resistance exercise, in that case, after that resistance exercise bout or workout, net protein balance becomes more positive. And what's interesting is that effect can last as long as approximately 2 days after the stimulus in untrained subjects. So resistance exercise is anabolic, and the effect can last for 2 days, especially if a person is relatively untrained. In trained persons, the muscle protein breakdown also tends to be decreased. So what tends to happen is resting muscle protein synthesis tends to be chronically elevated in resistance trained subjects, whereas muscle protein breakdown is decreased compared to untrained subjects. So if we consistently train in resistance exercise, we tend to be able to have a chronic muscle protein synthesis effect and a decreased muscle protein breakdown effect. Okay, so that's one of the benefits of consistently training in resistance exercise. Now, endurance exercise tends to be a little bit different. It tends to have less of an anabolic effect. So studies have indicated the endurance exercise effects on muscle protein synthesis are smaller in scale and duration relative to resistance exercise. And one of the questions is, well, okay, muscle protein synthesis tends to go up though, so which types of proteins tend to be synthesized? And I mentioned this before, but in endurance exercise, it tends to be more about increasing mitochondrial proteins and sarcoplasmic proteins rather than those of contractile proteins. And one of the studies that showed this was when they compared an endurance exercise regimen compared to an exercise regimen where they were doing leg extensions, but they were increasing the intensity or the weight or the force required. You could see the shift in the type of proteins that were being made in a force-specific response. So if you did high numbers of low-intensity leg extensions, it didn't really stimulate the fibrillar proteins to a high amount. But when that intensity and the weight was increased, there was a shift over. Now you're going from less synthesis of mitochondrial proteins to more about the contractile protein synthesis. Okay? We talked about that a little bit in the previous protein lecture. All right, so now let's talk about protein timing and basically consuming protein. And first one we'll talk about is in resistance exercise. So we'll look at that first. Previously, the focus was simply on protein amounts. when people realized they tended to have more lean body mass added when they ate more protein, that's all they looked at. Well, if you're going to try to add more muscle, consume significant amounts of protein. Then, fairly recently, some of the studies have been looking at, how about the timing? And also amounts of proteins may also be important. So that's what we'll talk about a little bit here, but then also overall protein. Although overall protein intake has been shown to be very important, some studies suggest that para-workout protein may be effective. In other words, what about protein intake around your workout? Before your workout and after your resistance exercise workout, how effective is that? Or can a person just eat protein throughout the day and still get the same benefits and not have to worry about when that protein is consumed? So let's look at pre-exercise protein intake relative to resistance exercise. So one of the things that a study looked at, they examined 6 grams of essential amino acid intake, and that is approximately equivalent to 15 grams of a high-quality protein. Okay. And they had 35 grams of sucrose just prior to a resistance exercise workout, and they found a 160% increase in muscle anabolism as compared to a similar drink ingested post-exercise. So in this case, they were saying, well, if a person consumes a combination of essential amino acids and carbohydrate before resistance exercise, they tended to have a better effect than post-exercise. And some other studies have also reported that. But overall, that's not completely consistent. So large variations between subjects suggested that individuals differ. In other words, that didn't work for everyone to consume it prior. And one of the proposed mechanisms was that hyperemia, which means the amino acid concentrations were significantly higher, and that's what caused the increase in protein synthesis. So it kind of depended on a few different things on whether or not that was effective for a particular individual. So it could have been their exercise regimen, could have been the actual amounts that were part of that. But so in some individuals, that can be effective. Now, they've also looked at the timing, the effects of protein intake during resistance exercise. And one study found co-ingestion of carbohydrate and casein stimulated muscle protein synthesis in an endurance resistance workout, and it stimulated muscle protein synthesis even though subjects ate before the workout. So one study said the person was consuming during the day, they ate before their workout, but if they consumed carbohydrate and casein during that workout, it stimulated muscle protein synthesis, even when this exercise bout was done when the subjects had eaten before. In this case, it was resistance exercise. And so they thought, well, maybe it's because they may have had enhanced muscle protein synthesis during the rest periods between the exercise sets. And at that point, because they were consuming amino acids, their amino acids in the blood were elevated. So during the sets, they were able to increase muscle protein synthesis. Even though it increased muscle protein synthesis, the net effect on muscle anabolism or accretion or addition was not significant. So that's another thing to keep in mind is, was the overall net effect beneficial? And overall, in this case, I'm going to say during resistance exercise, maybe not something needs to be focused on for resistance exercise. It may be better to do at other times. Numerous studies have indicated protein intake after resistance exercise is beneficial. For example, a study a while back showed the importance of consuming protein near the time of the exercise bout. So this is right after. In this case, they had men that were 74 years of age. They performed resistance training 3 times a week for 12 weeks and were randomly assigned to have a high protein from non-fat milk and soy, which was 10 grams of protein, 7 grams carbohydrate, 3 grams of fat, immediately after or 2 hours after each training session. So they either had the same protein right after, or they waited for 2 hours. And they found that those that were consuming it immediately after had significant increases in leg muscle mass. But waiting as little as 2 hours, they lost the effect. And other studies have also showed that may or may not be consistent. So not all studies showed positive effects, and this indicates important variables may differ between studies. And here's one of the points, I'll try to mention this a couple times. One very important effector is overall calorie intake. If a group is doing a research study and they're looking at protein intake effects, it's extremely important that the subjects get adequate amounts of protein and calories. If they do not get adequate amounts of calories, then you won't see the protein effect in general. In that case, the protein could be used for energy, maybe glucose production, and in that case, muscle protein breakdown may also be increased because of the lack of calories. So when you go through these studies, it's important that they do a good job at controlling dietary intake and that they record that and that those calories are in adequate amounts. Otherwise, the protein amounts are hard to kind of determine whether or not it's a good amount. So they have to be in positive calorie balance. And then the peri-workout nutrition may also cause variable effects. So that's another issue to think about. Okay. Now, protein, again, after resistance exercise, some studies aimed at effectiveness of protein also provided evidence for a timing effect. For example, in a case of milk versus soy, they had, this is quite a while ago, but Hartman et al. Reported lean mass gains in a large cohort. They had 56 young men after 13 weeks of intense resistance training. And they were testing whether milk was superior to soy or calories from carbohydrate at inducing gains in lean mass. So subjects were randomly assigned to consume 500 ml of fat-free milk. 500 mils is about 18 grams of protein. Or an isonitrogenous, isoenergetic, fat-free soy drink. So same amount of nitrogen, same amount of energy from soy. Or they had a carbohydrate control, which is immediately after resistance exercise and again 1 hour after exercise. In that study, the milk induced superior increases in type 2 fiber size and fat and bone-free mass compared to the soy. So those data illustrate that the intake of a high-quality protein within the first 2 hours after training is fundamental to maximize the hypertrophic adaptations. But the results also highlight a previously unrecognized benefit of milk proteins versus soy. Furthermore, the studies show that resistance exercise and feeding are synergistic, and the muscle protein synthesis is elevated to the greater extent within the initial hours after the exercise session. So it would seem that eating protein early offers substantial benefits. Okay, so eating right after is important because that's when muscle protein synthesis is up. And so it makes sense that that's the time to provide a good supply of amino acids. Now, one of the important things that some of these studies have indicated is, if we look at the last bullet point, however, because resistance exercise seems to make muscle more anabolically sensitive for an extended period of time, there are also positive effects of consuming protein at a later time as well. So that anabolic or nutrient sensitive effect appears to be relatively consistently found in research studies. So in other words, resistance exercise causes the muscle tissue to become more nutrient sensitive. In other words, it tends to kind of prime it for anabolic phase. And that's one of the advantages of consistently doing resistance exercise is it's important to consume protein and a mixed meal after, but also immediately after, but also throughout the day, we can also have benefits because that tissue tends to be more nutrient sensitive. So this is a full change from fasting. This is some of the data that we're looking at here. This full change from fasted state, resting conditions, and muscle protein synthesis after feeding and resistance. And then this says, note that the anabolic sensitizing effect of resistance exercise is greatest during the immediate acute recovery period. However, the sensitizing effect is still conferred more than 1 day after exercise. So the dashed line illustrates the summation of the fed response following exercise. So here we have the muscle protein. Remember, this is just synthesis, though. In the fed resting, we have muscle protein synthesis is up because of the feeding. And now we have 3 hours after the exercise and fasted. Right? Muscle protein synthesis is slightly up because of the exercise in this case. In this case, the combination of exercise and fed is significantly higher. Now, 24 hours later, look at muscle protein synthesis. It's down if they fasted, but in the fed state, muscle protein synthesis is elevated significantly. And this is the post-exercise sensitizing in this case. So both of these groups have exercised. This is without food. This is 24-hour fed. Okay? So to me, I think the message is, in this case, it's important that athletes consistently ingest good sources of protein throughout the day. They don't want to go long periods of time when they're in a consistent exercise program because they miss out on those opportunities to enhance the muscle protein synthesis. Okay, so I think it's important after a workout, but also consistently to take advantage of that kind of that sensitive status of the tissue by consistently consuming good sources of protein. So that's a good argument for multiple mixed meals containing protein sources and other nutrients, obviously, including carbohydrates. Okay, so that's a lot on resistance exercise. Now, what about endurance exercise? Individuals that do, let's say endurance bouts are maybe more endurance than resistance. So before I forget, let me just mention this. Let's say, for example, a person is doing a combination of both endurance and resistance exercise, which I would argue in a lot of cases is probably better than either or. In that case, what do? I think you've got to balance It's nice if you can give them adequate amounts of protein in order to meet the protein requirements for the resistance training, but you have to balance that with, can you also give them adequate amounts of carbohydrate to support their endurance training? If an athlete is doing this consistently and their calorie requirements and calorie expenditure is elevated, you can probably do both. And in that case, you should be able to meet high protein demands, but also the carbohydrate demands. And every person is different. And it might be that if you're working with someone, you have to try to track their performance and track their macronutrient intake and base their changes in performance. For example, if they are, their times or their strength are affected, then you're going to have to work on changing that macronutrient, changing the protein to carbohydrate ratios until their performance improves. And that is kind of an empirical situation where each individual has to be kind of considered in that case. So, okay, endurance exercise, protein ingestion. During the exercise, can protein add benefits compared to carbohydrates alone? So some studies have shown increased time to exhaustion when protein is also consumed during intense endurance exercise. And so these are relatively long endurance exercise bouts. For example, it's demonstrated that consumption of protein, and this is about 3.8 grams of protein with carbohydrate, 16 grams, given in small doses during 3 hours of intense cycling, increased time to exhaustion versus a placebo or carbohydrate only. So some studies have shown adding a little bit of protein helps. But some studies also show no benefit. So the results in this case of should endurance athletes, let's say they're doing a 3-hour cycling, relatively high intensity, or a run, should they consume protein? It's not really consistent. I would say overall, it's probably not a bad idea. It does help some people, as long as they're able to get adequate amounts of carbohydrate for fuel. Okay, so what about after the exercise? Can protein improve the effects of training? Most data seems to suggest that it does. Endurance exercise also seems to have a nutrient sensitizing effect, just like resistance exercise. So as a person trains, it's important that they consistently consume a nutrient-dense, adequate macronutrient diet in order to consistently recover and fuel for their exercise. So it's imperative that energy demands are met and paired with meeting protein needs. Okay, and one of the reasons, let's see if I have that here. Here's some of the adaptations that take place. So resistance exercise causes some effects, but endurance exercise and aerobic training tends to have these kind of 4 hallmark effects, and here they are. Number 1 is increased capillarization. So in other words, increased capillary density from endurance training. That's an important adaptation that helps them improve performance. And that can require additional nutrients, including protein intake. The second adaptation that's hallmark is mitochondrial biogenesis. Third one is increased glucose transporters and increased fat transporters that occur. So all of those adaptations require the turning over of proteins and the net addition of new proteins. So in other words, a positive net protein balance is required in order to support optimum adaptation. Those changes can help the person adapt to their endurance exercise and get better at it, but it's important that when those proteins are turning over, that the essential amino acids and amino acids are present in the muscle fibers and the tissues in order to allow those adaptations to take place. Otherwise, they can be compromised. So here's an example. Recent data demonstrate that after a 2-hour bout of cycling, participants who consume protein at 36 grams an hour, albeit at excessively high dose with carbohydrate during post-exercise recovery, had enhanced rates of muscle protein synthesis and were greater than after consumption of carbohydrate only after the same exercise bout. Now, that's a lot of protein, but it did kind of prove the point that it might help individuals adapt to that. Right, and remember also data reveals that aerobic exercise preferentially stimulates the synthesis of mitochondrial proteins. I went through that before. And again, it's really important that energy demands are met in those endurance athletes and paired with meeting protein needs. So let's talk a little bit about protein quality. So what types of proteins should you be recommending or should a person be consuming in this case? So protein quality is something that's talked about a lot, and one of the reasons we can kind of frame this in a larger picture is that post-protein and meal ingestion, hyperaminoacidemia occurs after consuming protein, and it is variable depending on the protein source. Right? So I think we know that when we consume protein, it's digested, it's absorbed, goes into the circulatory system, and so amino acid supplies in the blood go up. Now, how fast and how much those amino acid supplies goes up depends on a couple different factors. A few different factors, I should say. And we're going to talk about some of those now, but those are called basically amino acid kinetics, on how those amino acids are moving through the various pools in the body and how they and when they become available for protein synthesis. But for example, we've heard a lot about whey protein, and I've talked a lot about whey protein, but whey protein is a protein that goes into the blood quickly. And if we talk about overall whey protein, the chapter distinguishes different types of whey protein. So there's whey protein concentrates, where they essentially just use kind of I won't go into details, it's either a precipitation or a column purification method where they're separating the whey protein out from the other ones. So if you're looking for whey protein supplements, some of them are called whey protein concentrates, or sometimes they'll just say whey protein source. In that case, it's about 80% protein. The whey protein isolates, the whey is usually greater than 90% of the protein. And that's when the whey protein isolate tends to be a very pure form of whey. It tends to be very high in whey protein, very low in other proteins, and very low in things like lactose. And there's very little or no casein in there. And then sometimes you'll see where they'll say a whey protein hydrolysate. And that means that it is a partially digested whey protein that a person can consume, and it'll go into the bloodstream even faster. Overall, though, we generally say whey protein is a fast protein, hits the bloodstream quickly compared to the other major dairy protein, and that's casein. And but overall, the whey protein and dairy proteins are high-quality proteins. And another reason whey protein is so common and can be beneficial is it's very soluble. It goes into water, goes into lots of different solutions. Mixes pretty well, and the higher quality whey protein, especially the whey protein isolates, have very little flavor. So they're easy to flavor with other components. Let's say it's a smoothie or whatever food it's put in. The flavor is not an issue. So there's a couple different ways to look at protein quality. But overall protein quality, is affected mostly by the digestibility of a protein and also the amino acid profile, more specifically, the essential amino acid profile. The digestibility of animal proteins tends to be significantly better than plant proteins. And sometimes there's a 10 or 15% difference. Some plant proteins are only digested at 80–85%, whereas some animal proteins are digested at 90–95% efficiency. So sometimes those amino acids don't make it into the tissues, they don't get out of the gut, they're not digested or absorbed. So that's an effect. And also in general, the plant proteins have less essential amino acids per gram protein than the animal proteins. So there's a few different ways to look at this and calculate this. And I'm just going to look at one of them because this will make some of the points here. There is a calculation called the, and this is actually in your Gropper textbook if you want to look at this. This is called the Protein Digestibility Corrected Amino Acid Score. And it's a calculation that considers both digestibility and the essential amino acid profile. So you essentially compare a test protein to a reference protein. And in this case, for example, if we look at this equation, sorry, the formatting's not great, but this is essentially milligrams of a limiting amino acid in 1 gram of test protein divided by milligrams of the limiting amino acid in 1 gram of reference protein. The limiting amino acid is the essential amino acid in the lowest amount. That is the essential amino acid that is present in the lowest quantity in the food. It's called limiting because it could limit growth or protein synthesis. We talked about this in 328. So essentially, it's just the limiting essential amino acid that you're looking at. And you're comparing the test protein to a reference protein that has a high quality. And then you're factoring in digestibility. Okay? So obviously, if a protein has a relatively close essential amino acid amount to the reference protein and it's digestible, that can be a very high quality protein. And vice versa on both of those. So if you're considering making protein recommendations to individuals, one of the things to think about is to actually look at it in this way. And we'll come back to that in a minute. But so along this thought, let's keep going on this. And this is protein quality. And one of the unique amino acids in all of this, and I've mentioned this before, is leucine. And leucine is an essential amino acid. It's a branched chain amino acid, but just as importantly, it is a signaling molecule. And that's been known for quite a while now, but I think about, boy, I'm trying to remember when that paper came out. It was last year, potentially the year before, is when a group, it's actually Sabatini's group, that found the protein that leucine binds to in cells. For quite a while now, they've known that leucine has signaling properties. It can increase protein synthesis, and leucine can decrease muscle protein breakdown in tissues, specifically skeletal muscle. And it tends to be a kind of a marker for nutrient status in individuals that signals to muscle fibers when adequate nutrients, including essential amino acids, are present. And we've known that for a long time, but it wasn't until recently that they actually found the molecule that leucine binds to and confers that signaling ability. And in the interest of time, and for your sake, I didn't include a lot of that, but it's really, really fascinating. And now we're to the point where we kind of know how leucine works. But the leucine signaling pathway kind of runs in parallel to the insulin signaling pathway. So it's also important to note that as a person gets older, we tend to lose some of that, not only insulin, but also leucine signaling ability. And that's one of the reasons why protein requirements are more significant as we get older, even though the RDAs don't yet reflect that. They really should. Now, one of the things to think about is, well, if leucine is doing all of that, should we just look at proteins and their leucine content? So if we compare whey versus casein versus soy in this kind of scenario, one of the things that we can think about is how much leucine is there. Well, what about other plant proteins? What is their leucine content and how does that compare? So we'll look at that in a second. But all of this about leucine kind of led to this effect of, or this kind of hypothesis of what's called the leucine trigger. And this diagram shows that. If I'm just reading the legend, it shows after consumption of whey protein, which is higher in leucine content than soy or casein, there's a rapid increase in plasma leucine concentration. And this increase corresponds to the extent of stimulation of muscle protein synthesis. Okay, so far, based on what I've said, that should make sense. The more leucine that's in a protein source, the better it is at stimulating muscle protein synthesis. And that's what it shows here. Whey protein has significantly more leucine than either soy or casein. So here's whey and soy and casein. So it can stimulate muscle protein synthesis more. But one of the interesting things about this is, well, is there a threshold for leucine? In other words, if you just get to a certain point, are there not additional benefits if you go higher and higher? And it appears that that's the case. It appears that cells kind of have a leucine threshold. If we get that, we maximize stimulation, but additional leucine won't increase the stimulation of protein synthesis more. And I think that's an important point of this. The other thing to think about is, let's say, for example, a person has kind of a limited ability to consume significant amounts of protein. Should they just target those sources of proteins that are higher in leucine? And there's evidence in a lot of situations where that could be an appropriate way to go about it. So maybe in some cases, we do try to provide recommendations with protein sources that are higher in leucine, just to try to get that kind of minimal amount that maximizes stimulation. Not that the other proteins aren't effective, but some proteins might even be more effective than others. Now, why, how can we look at this kind of in a bigger picture? So these are the essential amino acids, and I don't know if you've realized this, but there is an RDA for each of the essential amino acids in humans. Now, these amounts are requirements for sedentary individuals. So how much is needed for those that exercise? So, for example, you can do this. You can take your kilograms of body weight, and this is how many milligrams of each of these essential amino acids you need. And if you go across the board here, look at these. Here's tryptophan, histidine. You go all the way across here. Here's lysine and leucine and valine. 3 of the 4 amino acids needed in the highest amounts are the branch chains. And here's leucine, has the highest RDA. And they've done a variety of different methods in order to determine this, but you can just kind of look at this. But remember, this is in sedentary individuals. So what if a person's exercising? Can we just say, well, can we keep all of these ratios or amounts relative to each other the same and just increase it? So rather than 0.8, we might say, well, they need 1.8 if they're a strength athlete, and we could just keep these amounts the same. I haven't seen data specifically looking at that, but in some ways that kind of stands to reason. These ratios might be inappropriate relative amounts. If we need more protein, we can just increase them across the board. And the point of that is, well, these essential amino acids up here could be examined in protein sources to determine amounts of protein sources in order to get to that specific amount. So there's still a lot of research that needs to be done in protein, and it's being done, and there's lots of companies and organizations that are interested in that. So I mentioned this before, but the protein research in sports nutrition is still strong, and it'll keep going that way, I think, for quite a bit of time. But just something to look at for you on that. Now, let's compare a couple things. I think that's a good way to do this. So here's an example. This is kind of not a great looking slide, but I kind of pieced this together through some product data sheets that I have. If we look on the left side of this, and here's a little plug for Glambia Nutritionals. This company is the one that is one of the leaders in protein sources. And even they are reaching out. They started out as a cheese company in Ireland and then got into the whey market and have made a huge impact in nutritional supplements, including whey. And they've been very generous with me, and as I develop products here and work with students in order to get them out to athletes and stuff, they've really been helpful to me in helping formulate and provide me with different variations on the product, and they have a million of them. So one of the ones that we use is one called Provon 292. That's a whey protein isolate. So this is whey protein over here, and this is the amino acid profile, 100 grams per powder of whey. And if you look over here, and this WPI is, boy, what is that? It's more than 90% of this 100 grams is protein. So it's a highly pure protein. Over here is a new one that they have that I'm I think starting to kind of look into on whether or not we're going to develop some products with this. This is a pea protein, and they call it Beverage Edge pea protein. And it is highly soluble. It's a purified form of pea protein. And I'm curious to try it now. I wouldn't have a few years ago. But if we look at amounts, let's just look at this. So basically whey protein versus a plant protein. If we go down through here, we can see the different amounts. And there's less protein overall here. I think this product is, and you can see that ROI, that says preliminary. This is a very new product for them. They haven't finalized their data on their product sheet yet. So this is still in the works, but these are amounts that they've come up with. But overall, this is about, I think it's about 80 or 85% protein compared to the more than 90% here. But look at the relative amounts. So if we go through here, let's just look at the branch chain. So here, for example, is valine. A lot more valine, 5.4 grams per 100 grams of valine in the whey. So this is one of the branch chains. Isoleucine, a lot more in the whey protein. And here's leucine, 9 grams versus 5.6 in the pea protein. So of those branch chain amino acids, there is a lot more in the whey protein than there is the pea protein. And overall, if you look at this, if you were to kind of characterize the essential amino acids, you'd find a lot more of the essential amino acids in the whey compared to the pea. Now, obviously, that has to do with protein differences and amino acid differences in the proteins of plant versus animals and genetics and all of that. Okay? But one thing to think about is, well, if there's a leucine threshold, and I need to get to that threshold, once I get to that threshold, I maximize protein synthesis in muscle fibers. Why don't I just eat a lot more of a particular protein that might have less? Why don't I just eat a lot more pea protein? Don't have to eat whey. Is that true? I'd say, in general, probably is. Person can just eat more and get to that level. And obviously, you know, you have to look at the ratios and everything, but that's one thing to think about. But now if you flip that, does a vegetarian have to eat more protein in order to maximize effects of exercise, especially resistance exercise? Do they need to eat more because they're eating plant proteins versus animal proteins? I would say more than likely. So when we look at that, the recommendations of protein, remember we're considering that's from a mixed diet. If we say grams of protein per kilogram body weight. Okay? So it's important that a person realizes protein quality and the types of protein sources are important. Okay, so just something to think about there. There's lots of different ways to look at this, and you can get these values. If you guys want to talk to me more about this later, that's happy to talk about it. But here's one of the things I was talking about. So protein quantity. If, for example, we consider, and a lot of these are, well, let me read this, they'll make it sound better than I will. The relationship between protein dose and muscle protein synthesis. 20 grams of egg protein maximizes the anabolic response to resistance exercise. There is no additional benefit from consuming 40 grams of egg protein. That is disappointing to some people that want to eat a lot of protein. Protein consumed in excess is either used for energy or wasted. So if we look over here, let's see, dose of egg protein. This is muscle protein synthesis. This is leucine oxidation. So you're kind of looking at the ratio of oxidation or kind of catabolism versus muscle protein synthesis. So with 5 grams, we have this percent change in muscle protein synthesis. 10 grams, look at this amount, right? Muscle protein synthesis up, but we're still oxidizing the same amount. So that's getting closer to a good solid ratio. Now look at this. At 20 grams of egg protein, we have what we're calling maximal stimulation. Like, what is that? Percent change is probably, what, 80 or 90%. And look at oxidation. It's gone up. So what that can mean is, what that might mean is, and this is unclear, no one knows this yet, but it looks like there's an amount that once you hit that, then more of the leucine becomes oxidized. And if we go over here, you can see now, what I mean by that is, now we've doubled the protein. We haven't got much of an increase in muscle protein synthesis, and yet there's a lot more leucine that's being oxidized. So we've hit our requirement for leucine for maximizing muscle protein synthesis, and now more and more of it is oxidized. As a matter of fact, some people have hypothesized that there's a relationship between this oxidation and stimulation, and that cells may be responding to this increase in oxidation, saying, okay, we have plenty of leucine, now use some of it for muscle protein synthesis. And they're thinking that maybe that has an effect on how much leucine actually stimulates the muscle protein synthesis. But one of the points to take from this is 20 grams of a high-quality protein is enough to maximize muscle protein synthesis in most people. Whether or not a person that weighs more or has more lean body mass needs more than 20 grams of protein is still unclear. So I'd say in general, you're fine recommending 20, maybe 25 grams of protein for an individual to maximize effects. And again, this is, you know, probably post-exercise, or even if it's through the day, there's not really a need for them to take in that much more protein in any given time. Sometimes they need to, but that's maximum effects. again, this is kind of looking at this is how much protein is needed. Theoretical model illustrating the dose of protein needed to maximize muscle protein synthesis after an acute bout of resistance exercise. Note this thesis has never been systematically tested and as such is purely speculative. So here's protein dose in grams. So for example, here's our 15 grams. What they're saying is, as a person increases in body weight, do they need more muscle protein? So this theoretical model, and you could say, even in that case, here's your protein dose. If a person weighs 100 kilograms or 220 pounds, 25 grams of protein may be more than enough. And this is true for men and women. Women benefit significantly from the protein doses and the same. Now, they probably do need a little bit less. So, for example, maybe 15 grams is enough in most female athletes compared to 20 grams is enough for most male athletes. But again, still a lot of work to be done in this, and I'm sure we'll see it. So what kind of foods contain 20 grams of high-quality protein? 500 mils or 2 cups of fat-free milk. And the fat-free milk has, remember, obviously combination of whey and casein, but 3 ounces of beef, 2.5 ounces of chicken or turkey, 3/4 cup of cottage cheese. So not that hard to get at 20 grams of high-quality protein in food amounts, I would say. A little bit challenging. So, for example, in this case, is another reason why some supplements are so common. It's if a person is exercising, they're finishing a run, finishing a cycling bout, finishing a game or match or whatever, it's easier to carry around supplements in some of those cases than it is to actually pack food for some individuals. So protein and endurance exercise, is the extra protein needed for endurance athletes? And then how do we determine amounts required? Why might more be required? So this kind of goes to some of the things we've talked about before. And this is compared to resistance exercise. And I would say in general, endurance athletes obviously do need more than sedentary individuals. How to determine amounts required. They've done nitrogen balance. They've done some tracer studies where they've looked at muscle protein synthesis, quite a few different ways, show that they do need additional protein compared to sedentary. And again, they probably, in this case, need additional protein for changes in body composition, but also changes in amino acid oxidation during that exercise. And also, of course, some of the amino acids are needed to effectively replace and enhance mitochondrial proteins for energy production as well. So here are the amounts, daily protein recommendations for endurance and resistance training athletes. I gave you these numbers before. Endurance, 1.2 to 1.4. Grams of dietary protein per kilogram body weight per day. And then resistance or strength athletes, about 1.6 to 1.7. Sometimes you'll see 1.6 to 1.8. So significantly more for the resistance training athletes. And again, I mentioned before, but a lot of athletes do both. So you kind of have to balance those different amounts of proteins with carbohydrates. What about single amino acids or proteins? Could supplementation with individual amino acids be effective? The textbook or this chapter mentions arginine, glutamine, and leucine. Arginine is an amino acid that is generally needed for significant growth. In some animals, arginine is a essential amino acids. For us, it's not. So in general, we can make adequate amounts of arginine in order to not need to take additional amounts in single forms as a supplement. And so the data on that is at best ambiguous. And it's the same for glutamine. The proposed mechanism for arginine and glutamine is they increase growth hormone levels. And glutamine, again, I'd say the data is ambiguous. So it's not consistently proven to be a beneficial supplement to take glutamine by itself. Now what about leucine? All of the benefits of leucine that we talked about and signaling. But one thing to keep in mind is it's without the other essential amino acids and the non-essential amino acids, leucine would not have maximal effects. So I'd say in general overall, it's better to take leucine as part of a high quality protein source. Now, one thing that you might see down the road is combinations of amino acids with additional leucine. So for example, you might see, and some companies are already making this, they'll make a whey protein with additional leucine added. So I think you'll see more and more combinations of these. But in general, overall, I still think it's better to take a food source or something close to a food source or similar to a food source to get a combination of a good amount of leucine and the other amino acids. So key points: exercise increases protein demands. I mean, there's lots of examples of that, and varying types of exercise will increase that. The timing of the protein should be considered. In general, I think we can say it's probably beneficial to take protein post-exercise in a variety of modes of exercise. So if a person's gonna, kind of prioritize their protein intake, it should be post-exercise. And then kind of build out from there, whether or not they want to take it before. That might be effective. During is potentially effective in some cases, but I'd probably say after would be the priority. And then consume it consistently throughout the day. Amounts of the protein are important and becoming more defined, so we'll see more on that as we go. And types of protein and quality may affect effects. That's great English. May have beneficial effects, and all other essential nutrients must also be considered for optimal health and performance effects. So we got to remember carbohydrates. If carbohydrates aren't in adequate amounts, it compromises protein metabolism. And then, of course, overall calories are really important. And one of the benefits for athletes is they increase their energy requirements, and that allows them to consume more nutrients across the board. So we want to make sure that it is a diverse diet where we're trying to get all of our nutrients, including protein, I would say, from foods first, and supplements if necessary. But obviously, health and performance can go hand in hand, and so it's important that an overall nutrient-dense, healthy diet, including good quality protein sources, are considered to be the best recommendations. Okay, I'm going to stop there. Sorry this went a little long. Thank you.